Good day everyone! For today's video, we're going to discuss or to report the discrete Fourier transform. But before we dig into our proper discussion, let us introduce ourselves first. My name is Bongoyan and I'm 7 and I'm Jorge. And now, let's proceed to our discussion. Objectives. First, students will be able to understand the DFT. Second, bring to the students' attention the importance and the advantages of the DFT. Third, students will be able to solve the DFT and IDFT. Fourth, student will be able to solve the DFT as a linear transformation. Fifth, examine its properties. Introduction. The discrete Fourier transform or DFT operates on a finite set of numbers or a finite segment of a discrete signal. Physically, the DFT of a discrete time function xn may be viewed as its frequency domain representation and used as a tool to approximate the DFT, FST, or the spectrum of the continuous time function xr from which xn is produced. Mathematically, the DFT may be formulated by extending the classical Fourier transform of continuous time signals to a finite length discrete time sequence through sampling and windowing. Alternatively, the DFT can be introduced as an operation specified by a transformation matrix that converts a sequence xn to another sequence xk of the same length.
The discrete Fourier transform. The DFT transform a finite length sequence xn 0 less than or equal to n less than or equal to n minus 1 into another sequence xk 0 less than or equal to k and k less than or equal to n minus 1 of the same length, where xk is equal to summation of n equals to 0 to n minus 1 x of n e raised to negative j2 pi kn over capital N, where k varies from 0 to n minus 1. xk is called the endpoint DFT of xn, and xn is called the inverse discrete Fourier transform or IDFT of xk. The latter may be recovered from xk by xn equals to 1 over capital N summation of k is equals to 0 to n minus 1 x of k e raised to j2 pi kn over capital N, where n varies from 0 to n minus 1. Customarily, xn represents a function in the time domain and xk is referred to as its representation in the frequency domain. The sequences xn and xk always begin with the 0 term. They may be real values or complex number. In this chapter, we will be focused mostly on a real valued xn.
Example of DFT. Compute the 4-point DFT of the sequence x of n is equals to 1, 2, 1, 2. The length of the sequence xn is 1, 2, 3, 4, and capital N is also 4. So the DFT of xn is xk is equals to summation of n equals to 0 to n minus 1 x of n e raised to negative j 2 pi kn over capital N, where k varies from 0 to n minus 1. Here capital N is 4. Substitute capital N to 4. So our equation xk is equals to summation n equals 0 to 4 minus 1 xn e raised to negative j2 pi kn over 4. xk is equals to summation of n is equals to 0 to 4 minus 1 is 3 xn e raised to negative j2 pi kn over 4, where n is equals to 0 to 3. And now let's expand the summation. xk is equals to x of 0 e raised to negative j2 pi k times 0 over 4 plus x of 1 e raised to negative j2 pi k times 1 over 4 plus x of 2 e raised to negative j2 pi k times 2 over 4 plus x3 e raised to negative j2 pi k times 3 over 4. So we all know that anything multiplied by 0 is 0. So x of 0 e raised to 0 plus x of 1 e raised to negative j pi k over 2 plus x of 2 e raised to negative j pi k, because we cancel the 2 and 4 plus x of 3 e raised to negative j3 pi k over 2. And now let's substitute the value of 0, x of 0, where so x of 0 is equals to 1, so e raised to 0 is equals to 1 plus 2, x of 1 is 2 plus 2 times e raised to negative j2 pi k over 2 plus x of 2 is 1 times e raised to negative j pi k plus x of 3 is 2 times a raised to negative j3 pi k over 2. 1 times 1 is 1 plus 2 is 2 times a raised to negative j pi k over 2 plus 1 times e raised to negative j pi k is e raised to negative j pi k plus 2 times e raised to negative j 3 pi k over 2. And here are new equation. And now let's solve for k. When k is 0, x of 0 is equals to 1 plus 2 times a raised to negative j pi times 0 over 2 plus e raised to negative j pi times 0 plus 2 times a raised to negative g3 pi times 0 over 2. Copy 1 plus 2 times e. Anything multiplied by 0 is 0. So 2 times e raised to 0 plus e raised to 0 plus 2 times e raised to 0. X of 0 is equals to 1 plus 2. The value of e raised to 0 is 1 plus 1 plus 2 times 1. X of 0 is 1 plus 2 plus 1 plus 2 is 6. So our x of 0 is 6. When k is equals to 1, x of 1 is equals to 1 plus 2 times e raised to negative g pi times 1 over 2 plus e raised to negative g pi times 1 plus 2 times e raised to negative g 3 pi times 1 over 2. X of 1 is equals to 1 plus 2 times e raised to negative g pi over 2 plus e raised to negative g pi plus 2 times e raised to negative g3 pi over 2. X of 1 is equals to 1 plus 2. We all know that e raised to positive negative j theta is equals to cos theta positive negative g sine theta. So 1 plus 2 times cos pi over 2 minus g sine pi over 2 plus cos pi minus g sine pi plus 2 times cos 3 pi over 2 minus g sine 3 pi over 2. X of 1 is equals to 1 plus 2 times cos pi over 2 is 0 and sin pi 2 is negative 1 or negative j plus cos pi is equals to negative 1 and sin pi is minus 0 plus 2 times cos 3 pi over 2 is 0 plus sin 3 pi over 2 is j. So x of 1 is 1 plus 2 times 0 is 0, 2 times negative j is 2j plus negative 1 plus 2 times 0 is 0 plus 2 times j is 2j. And now we have 1 minus 2j minus 1 plus 2j is equals to 0. So our x1 is 0. When k is equals to 2, x of k is equals to 1 plus 2 times a raised to negative g pi times 2 over 2 plus a raised to negative g pi times 2 plus 2 times a raised to negative g 3 pi times 2 over 2. X of 2 is equals to 1 plus 2 times a raised to negative g. We cancel 2, so we have 2 times a raised to negative g pi plus e raised to negative j 2 pi plus 2, cancel 2, we have 2 times a raised to negative j 3 pi. So we know that e raised to negative positive j theta equals to cos theta positive negative j sine theta in trigonometric function. So x of 2 is equals to 1 plus 2 cos pi minus g sine pi plus cos 2 pi minus g sine pi plus 2 times cos 3 pi minus g sine pi g sine 3 pi. So 1 plus 2 cos pi is equals to negative 1 and sin pi is equals to 0 plus cos 2 pi is 1 minus sin 2 pi is 0 plus 2 cos 3 pi is negative 1 and sin 3 pi is negative 0. So 1 minus 2 minus 0 plus 1 minus 2 minus 0 is equals to 2 minus 4. 2 minus 4 is equals to negative 2. So our x of 2 is negative 2. When k is equals to 3, x of 3 is equals to 1 plus 2 times e raised to negative g pi times 3 over 2 plus e raised to negative j pi times 3 plus 2 times e raised to negative j 3 pi times 3 over 2. X of 3 is equals to 1 plus 2 times e raised to negative j 3 pi over 2 plus e raised to negative j 3 pi plus 2. 3 times 3 is 9, so we have 2 times e raised to negative j 9 pi over 2. So we know that in trigonometric function, it is to positive negative j pi is equals to cos pi plus minus g sin pi. So x of 3 is 1 plus 2 cos 3 pi over 2 minus g sin 3 pi over 2 plus cos 3 pi minus g sin 3 pi plus 2 cos 9 pi over 2 minus g sin 9 pi over 2. X of 3 is equals to 1 plus 2 cos 3 pi over 2 is 0, sin 3 pi over 2 is negative j into negative 1 plus cos 3 pi is negative 1 minus g sin pi 3 pi is 0 plus 2 cos 9 pi over 2 is 0 and g sin 9 pi over 2 is negative j into positive 1. So x of 3 is 1 plus 2j minus 1 minus 2j is 0. So our x of 3 is 0. So the 4-point DFT of the sequence x of n is equals to 1, 2, 1, 2 is x of k is equals to 6, 0, negative 2, 0. Example of IDFT. Compute the 4-point IDFT of the sequence x of k is equals to 6, 0, negative 2, 0. The length of the sequence xk is 1, 2, 3, 4 and capital N is also 4. So the DFT the IDFT of xk is x of n is equals to 1 over n summation of k is equals to 0 to n minus 1 xk e raised to positive j2 pi kn over capital N, where n bar is from 0 to n minus 1. Let's substitute the value of capital N, which is 4. So x of n is equals to 1 over 4 summation of k is equals to 0 to 4 minus 1 x of k e raised to positive j2 pi kn over 4. X of n is equals to 1 over 4. 4 minus 1 is 3. So 1 over 4 summation of k is equals to 0 to 3. X of k e raised to positive j2 pi kn over 4, where k varies from 0 to 3. So let's expand the summation. X of n is equals to 1 over 4. X of 0 e raised to positive g2 pi times 0 n over 4 plus x of 1 e raised to positive j2 pi times 1 n over 4 plus x of 2 e raised to positive 2 pi times 2 n over 4 plus x of 3 e raised to positive j2 pi times 3 n over 4. So we all know that anything multiplied by 0 is 0. So x of n is equals to 1 over 4 x of 0 e raised to 0 plus x of 1 cancel e g pi n over 2 plus x of 2 cancel e j pi n plus x of 3 cancel e raised to j3 pi n over 2. Now let's substitute the value of x0, which is x of 0, x of 1, x of 2, and x of 3. So x of n is equals to 1 over 4. Then the value of x of 0 is 6. Then the value of e raised to 0 is 1. Plus the value of x of 1 x of 1 is 0 times e raised to positive j pi n over 2 plus the value of x2 which is negative 2 e raised to positive j pi n plus the value of x3 is 0 times e raised to positive j3 pi n over 2. So x of n is equals to 1 over 4. 6 times 1 is 6 plus 0 times, we all know that anything multiplied by 0 is 0 plus negative 2 times aj pi n, that's 0. So x of n is equals to 1 over 4. 6 minus 2 times aj pi n. Here are new equation. When n is equals to 0, x of 0 is equals to 1 over 4 times 6 minus 2 times a raised to positive pi times 0. So x of 0 is equals to 1 over 4 times 6 minus 2. We all know that anything multiplied by 0 is 0. So 6 minus 2 times a raised to 0. X of 0 is equals to 1 over 4 times 6 minus 2 times 1. The value of a raised to 0 is 1. So 6 minus 2 times 1. X of 0 is equals to 1 over 4 times 6 minus negative 2 times 1 is negative 2. X of 0 is equals to 1 over 4 times 4. So x of 0 is equals to 4 divided by 4 is 1. So our x of 0 is 1. When n is equals to 1, x of 1 is equals to 1 over 4 times 6 minus 2 times a j pi times 1. X of 1 is equals to 1 over 4 times 6 minus 2 e j pi. X of 1 is equals to 1 over 4 times 6 minus, we all know that e raised to positive negative j theta is equals to cos theta positive negative j sin theta in trigonometric function. So x of 1 is equals to 1 over 4 times 6 minus 2 times cos pi plus j sin pi. X of 1 is equals to 1 over 4 times 6 minus 2. Cos pi is negative 1 and sin pi is 0. X of 1 is equals to 1 over 4 times 6 plus 2 minus 0. X of 1 is equals to 1 over 4 times 8. X of 1 is 8 divided by 4 is 2. So our x of 1 is 2. When n is equals to 2, x of 2 is equals to 1 over 4 times 6 minus 2 times a raised to positive pi times 2. X of 2 is equals to 1 over 4 times 6 minus 2 times a e raised to negative j 2 pi. X of 2 is equals to 1 4 times 6 minus 2. We all know that e raised to positive negative j theta is equals to cos theta positive negative j sin theta. So x of 2 is equals 1 over 4 times 6 minus 2 times cos 2 pi plus j sin 2 pi. X of 2 is equals to 1 over 4 times 6 minus 2 cos 2 pi is 1 plus j sin 2 pi is 0. X of 2 is equals to 1 over 4 times 6 minus 2 minus 0. X of 2 is equals to 1 over 4 times 4. So our x of 2 is 1. When n is equals to 3, x of 3 is equals to 1 over 4 times 6 minus 2 times e raised to positive j pi times 3. X of 3 is equals to 1 over 4 times 6 minus 2 times e raised to positive 3 pi. X of 3 is equals to 1 over 4 times 6 minus, we all know that e raised to negative positive j theta is equals to cos theta positive negative j sin theta. So x of 3 is equals to 1 over 4 times 6 minus 2 times cos 3 pi plus j sin 3 pi. X of 3 is equals to 1 over 4 times 6 minus 2. Cos 3 pi is negative 1 and sin 3 pi is 0. X of 3 is equals to 1 over 4 times 6 plus 2 plus minus 0. So x of 3 is equals to 1 over 4 times 8. X of 3 is equals to 1 times 8 is 8 over 4. So x of 3 is 8 divided by 4 is 2. So our x of 3 is 2. So the 4-point IDFT of the sequence x of k is equals to 6, 0, negative 2, 0 is x of n equals to 1, 2, 1, 2.
DFT as a linear transformation. Now, we will define the new term omega as omega n equals e raised to negative j2 pi over capital N. This is called as middle factor. Middle factor makes the computation of DFT a bit easy and fast. Using middle factor, we can write equation of DFT and IDFT as follows. For DFT, xk equals summation of n equals to 0 to n minus 1. X of n omega n to the power of kn, where k varies from 0 to n minus 1. And for IDFT, xn is equals to 1 over capital N, summation of k is equals to 0 to n minus 1, x of k omega n to the power of negative kn, where n varies from 0 to n minus 1. The Twiddle factor is denoted by omega and is given by omega n equals e raised to negative j2 pi over capital N. Now, the discrete time sequence x of n can be denoted by xn. Here, capital N stands for n-point DFT. Range of n is from 0 to n minus 1. Xn can be represented in the matrix form as follows, where n varies from 0 to negative. N varies from 0 to n minus 1. Now, the DFT of x of n is denoted by x of k. In the matrix form, x of k can be represented as follows, where k varies from 0 to n minus 1. We can also represent omega n to the power of kn in the matrix form. Remember that k varies from 0 to n minus 1 and n also varies from 0 to n minus 1. Note that each value is obtained by taking multiplication of k and n. For example, if k is equals to 2 and n is equals to 2, then we get omega n to the power of kn is equals to omega n to the power of 2 times 2 is equals to omega n to the power of 4.
To obtain this value, we multiply k by n. So when k is 0 and n is 0, we get omega n raised to 0. So we all know that anything multiplied to 0 is 0. That's why we get omega n to 0 in the first column and omega n raised to 0 in the first row. So when k is 1 and n is 1, 1 times 1 is 1. So we get omega n raised to 1. When k is 1 and n is 2, 1 times 2 is 2. So we get omega n raised to 2. When k is 1 and n is 3, 1 times 3 is 3. So we get omega n raised to 3. So when k is 2, then n is 1. 2 times 1 is 2, so we get omega n raised to 2. When k is 2 and n is 2, 2 times 2 is 4, so we get omega n raised to 4. When k is 2 and n is 3, 2 times 3 is 6, so we get omega n raised to 6. When k is 3 and n is 1, we get omega n raised to 3. When k is 3 and n is 2, 3 times 2 is 6, so we get omega n raised to 6. When k is 3 and n is 3, 3 times 3 is 9, so we get omega n raised to 9. And to get the value of this, we will use the formula of Seidel factor, which is omega n is equals to e raised to negative j 2 pi over capital N. So the value of omega n raised to 0 is omega, and our capital N is 4, raised to 0 is equals to e raised to negative j 2 pi over 4. Then multiply by 0 is equals to, so we all know that anything multiplied by 0 is 0. So e raised to 0 is 1. So our omega 4 raised to 0 is 1. And since we have lots of omega n raised to 0, in column 1, all are omega 0, omega n raised to 0. So the value of omega n raised to 0 is 1. So omega 0 is 1, omega 0 is 1, omega raised to 0 is 1, omega raised to 0 is 1. In a row, we have omega raised to 0 is 1, omega raised to 0 is 1, omega raised to 0 is 1. So now we will solve omega n raised to 1 equals to e raised to negative j 2 pi over capital N. So our capital N is 4 raised to 1, e raised to negative j 2 pi over 4 times 1. E cancel j pi over 2. So we all know that e raised to positive negative j theta is equals to cos theta minus positive negative j sin theta. So e cos pi over 2 minus g sin pi over 2. So cos pi over 2 is 0. Then g sin pi over 2 is j. So 0 minus j is negative j. So our omega 4 raised to 1 is negative j. Omega n raised to 1 is negative j. So now we will solve omega 4 raised to 2. E raised to negative j 2 pi over 4 times 2 is equals to e raised to negative j 2 times 2 is 4, then 4 divided by 4 is 1. So we get pi. So we all know that e raised to positive negative j theta is equals to cos theta plus minus j sin theta. So cos pi minus j sin pi. Cos pi is equals to negative 1 and g sine pi is equals to 0. So negative 1 minus 0 is negative 1. So our omega 4 raised to 2 is negative 1. Omega 4 raised to 2 is negative 1. Next is omega 4 raised to 3 is equals to a raised to negative j2 pi over capital N or 4 times 3 is equals to e raised to negative j, cancel, pi times 3 is 3 pi over 2 is equals to, then the trigonometric function which is cos 3 pi over 2 minus j sine 3 pi over 2. So cos 3 pi over 2 is equals to 0. Then g sine 3 pi over 2 is equals to negative j. So 0 minus negative j is positive j. So our omega 4 raised to 3 is positive j. Omega 4 raised to 3 is positive j. Omega raised to 3 is positive j. So let's solve for omega 4 raised to 4. So equals to e raised to negative j2 pi over 4 times 4. E raised to negative j cancel 4 pi over 2 is equals to trigonometric function which is cos 4 pi over 2 minus j sine 4 pi over 2. Cos 4 pi over 2 is 1. Then g sine 4 pi over 2 is 0. So 1 minus 0 is 1. So our omega 4 raised to 4 is positive 1. Omega raised to 4 is positive 1. And now let's solve for omega 4 raised to 6. E raised to negative j 2 pi over 4 times 6 is equals to e cancel 6 times pi is 6 pi over 2. Trigonometric function cos 6 pi over 2 minus g sine 6 pi over 2. Cos 6 pi over 2 is negative 1 minus g sine 6 pi over 2 is 0. So negative 1 minus 0 is negative 1. So our omega 4 raised to 6 is negative 1. Omega raised to 6 is negative 1. So now let's solve for omega 4 raised to 9. E raised to negative j 2 pi over 4 times 9 is equals to e raised to negative j, cancel. 9 times pi is 9 pi over 2. Trigonometric function, cos 9 pi over 2 minus j sine 9 pi over 2 is equals to cos 9 pi over 2 is 0. Then g sine 9 pi over 2 is negative j. So 0 minus negative j is negative j. So our omega 4 raised to 9 is negative j. Omega raised to 9 is negative j.
Thus, DFT can be represented in the matrix form as xn is equals to omega n xn. Similarly, IDFT can be represented in the matrix form as xn is equals to 1 over capital N omega n xn. Here, Wn is the complex conjugate of Wn.
Example of a matrix DFT. Calculate the 4-point DFT of 4-point sequence x of n is equals to 1, 2, 1, 2. Solution. Our formula is xn is equals to omega n times xn. So our endpoint DFT is 4. Then we get the value of this, which is here. So we multiply x4, which is this 1, 2, 1, 2. So 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. Negative j times 2 is negative 2j. Negative 1 times 1 is negative 1. J times 2 is 2j. 1 times 1 is 1. Negative 1 times 2 is negative 2. 1 times 1 is 1. Negative 1 times 2 is negative 2. 1 times 1 is 1. J times 2 is 2j. Negative 1 times 1 is negative 1. Negative j times 2 is negative 2j. So 1 plus 2 is 3, plus 1 is 4, plus 2 is 6. 1 minus 1 is 0. Negative 2j plus 2j is 0. 1 minus 2 is negative 1. 1 plus 1 is 2. Negative 2 minus 2 is 4. So negative 4 minus 2 is negative 2. So 1 plus 2j minus 1 minus 2j is 0. So the 4-point DFT of a matrix is 6, 0. X of 4 is equals to 6, comma 6, comma 0, comma negative 2, comma 0. Example of a matrix IDFT. Calculate the 4-point IDFT of 4-point sequence x of k is equals to 6, comma 0, comma negative 2, comma 0. So solution. So the formula of matrix IDFT is x4 is equals to 1 over 4 conjugate of omega 4 x4. So kanina ang aton omega 4 is ini. So since may siya conjugate, babalyuan taan signs ang aton imaginary number, which is ang negative j magiging positive j, then ang positive j magiging negative j, tapos ang positive j is magiging negative ang negative j magiging positive. So sa aton formula, x4 is equals to 1 over 4 times ang conjugate of omega 4 which is inina, then aton x4 which is 6, 0, negative 2, and 0. Then we multiply conjugate of 4 times x of 4 which is 1 times 6 is 6, 1 times 0 is 0, 1 times negative 2 is negative 2, 1 times 0 is 0, 1 times 6 is 6, positive j times 0 is 0, negative 1 times negative 2 is positive 2, negative j times 0 is 0, 1 times 6 is 6, negative 1 times 0 is 0, 1 times negative 2 is negative 2, negative 1 times 0, negative 1 times 0 is 0, 1 times 6 is 6, negative j times 0 is 0, negative 1 times negative 2 is positive 2, then j times 0 is 0. So copy 1 over 4, 6 plus 0 minus 2 plus 0 is 4, 6 plus 0 plus 2 minus 0 is 8, 6 minus 0 minus 2 minus 0 is 4, 6 minus 0 plus 2 plus 0 is 8. So 1 over 4 times 4 is 1. 1 over 4 times 8 is 2. 1 over 4 times 4 is 1. And 1 over 4 times 8 is 2. So the 4-point IDFT of this sequence is x4 is equals to 1, comma 2, comma 1, comma 2.
Properties of this. First, linearity. The n-point DFT of AX in AX to the n plus by quantity n AX times K plus by times K for any x n and yn of the same length and any constant at A and B. Xn is DFT of xk, yn, yk, AX times n plus by times n is DFT of AX times K plus by. For you to say xn equal xk, then xn equals to x times n plus n for n. Xk equals to x times k plus n. How to prove the DFT properties.
This is linearity. If DFT x sub 1 at n is equal to x sub 1k. DFT x sub 2 times n is equal to x sub 2 where the DFT AX
equals to symmetry n equals to 0 and n equals x of 1 is 2 pi n where 0 is equal to k and k is
The third properties of DFT is empty. As we have seen, the input DFT the duration sequence x constant then f less than equal n is equivalent to an input DFT periodic sequence x d raised to xp times n, creating an which is equal vertically extended x times n and x times equals to symmetry infinite 1 raised to equals to negative x times n minus ln. Now suppose that we have a periodic sequence x n by k units to the right as we apply another periodic sequence.
the circular symmetry of x is equals to x is equals to is equals to
sub 3.5